Yeah, so my goal in this lecture is just to show you a couple of really, really lovely ideas that that get to very nice results in additive combinatorics. So the first was this theorem of Elikesh. The next one is going to be a recent breakthrough due to DeVos. And DeVos, and this is, I'm so bad with dates. I mean, DeVos proved the so-called finite field KAIST problem, and that's in like 2012 or something, or maybe 2011. Oh no, rats! Sorry, I just lost my page and I don't have the internet. Oh, there we are. Okay, it's back. Okay. Okay. So I'm going to sort of tell you a little bit of the real the real problem, and by real I mean real number type real. So I'm going to say this problem originally about the real numbers, and there's still a very famous conjecture here. But then we're going to jump to the finite field analog, which is a very natural kind of additive combinatorics type problem, and we'll see a very lovely solution to it using some polynomial techniques. So there's this old conjecture about concerning turning a line segment around in the plane. So the idea is you have a unit line segment, it's sitting in the Euclidean plane, and you'd like to turn it around. Only you want to do it in a set with very little area, right? So you'd somehow like to take this. I mean, obviously you could, if you take a circle with this diameter, you could just turn the thing right around, and you could do some things that are, slightly less naive. I mean, here's, I don't know how well everyone can see, but here's a little line segment turning around in a little triangular shape. And the question was, how small, how much area do you actually need to turn your unit line segment around? And and the answer, due to Besekovich, is epsilon. So for any epsilon, there's a set of measure epsilon in the plane, so that you can take any line segment and turn it around. And they look kind of weird and long and skinny. At the end of the day, that probably isn't actually. This is somehow not actually all that deep and difficult. The interesting question is not like the Lebesgue measure of your set, but the Hausdorff dimension. So there are these things like Hausdorff dimension that measure somehow the complexity of your set. And although these sets that you can take this unit line segment and turn it around, and you can make them with very small area, they're very messy sets, and they're going to have Hausdorff dimension basically too. So there's a general conjecture about this. Actually, sort of turning it around is a little inconvenient too. A nicer definition of a set is a KAIST set. So a KAIST set is, say, in R to the D, is a set of points containing a unit line segment in each direction. Right, and so let me just sort of indicate to you very quickly with this Wikipedia page a way you could make one of these things. So here we've started with just an equilateral triangle. We've chopped it in half, and we've overlapped those two. Well, your triangle should be big enough to contain this should be a unit line segment here. And then we've just chopped the triangle in half, and then you repeat, and you overlap, and you overlap, and you you keep making sort of smaller things and overlapping them more. And by proceeding in this manner, you can get sets with arbitrarily small area that still contain a unit line segment in every direction. And you can do similar things in higher dimensions. The serious problem from the analyst perspective is to show that KAIST sets have big Hausdorff dimension. And that's, that's a very serious, very significant problem that I know nothing about. There was a finite field analog of this that was conjectured some time ago, and this was promoted very heavily by people like Terry Tao a number of years ago, in part because it's a purely combinatorial problem. It's finite point sets, and it was kind of hoped for that. That one, that it might be more tractable in some ways, and two, that it might give some insight into the continuous case where you care about Hausdorff dimension. What's happened is the finite field version has been solved by a lovely, lovely little polynomial argument. That's what I'm going to present. As far as anyone can tell, this yields absolutely no insight into the original problem, but whatever. Anyway, it's a nice question, and it has a particularly nice solution, and it's one of these nice cases where you see some kind of simple properties of polynomials creeping in to give us the answer. So I wanted to do a polynomial type theorem. Oh yeah, actually this worked well. Let me write down the theorem over here as well. So of course for finite field. So I'm now going to be looking at a finite field. I think for the rest of this lecture, f sub q will be my finite field of order q. And I'm going to be interested in this n-dimensional vector space, fq to the n, and now what's going to be the analog of containing a? So I'm going to be interested in something that's vaguely like a KAIST set. So I want a subset of points of fq to the n. Only what I'm going to ask for is that my set contains a whole affine line in every direction. Clear what I mean? Right? So I mean, I'm in this vector space. For any vector, every vector gives you a direction. I'd like my set to contain an affine line in every direction. And the conjecture here is that, so the finite field KAIST conjecture that I'm going to be presenting the proof to was that any finite field KAIST set, so any subset of fq to the n that contains an affine line in every direction must be large. And let me say the precise thing. So the theorem here, this is due to DeVos, is that if A is a subset of fq to the n, if this contains an affine line in every direction, then it has to be large. So this has to be at least q plus n minus 1 choose n. So if you're thinking now of fixing the dimension but letting the size of the field grow, right? So if you're thinking of n as fixed and q now as growing, then this looks like q to the n over n factorial. Right? So if n is fixed and q is growing, then this quantity looks like q to the n over n factorial roughly. Q to the n is the number of points. So this is telling you that any set with a 1 over n factorial with size that any set containing an affine line in each direction must have size at least 1 over n factorial. Right. So right. So again, so sort of if we've fixed the dimension that we care about, and we're asking what happens over large fields, this is telling us that if you're going to pick up a set of points that contains an affine line in every single direction, you're going to have size at least 1 over n factorial times the total number of points. Okay. And so we can go on. Okay. So as I say, this is the this was the finite field KAIST conjecture. And this was proved, I'm not 100% sure of when this was proved, but it's just a couple of years ago by Zeev Dvir. I believe that Zeev Dvir was a graduate student at the time. Right, so the proof, as I said, is going to go through some very kind of simple properties of polynomials over finite fields. And I just want to sort of say a few of these things to sort of remind us. So I'm going to be interested in fq of x1 up to xm, right? So these are formal polynomials in the variables x1 up to xm, where the coefficients are from my field. So, well, I can always express these things. So if p is in here, I can always write p of x1 up to xm, or sorry, this is going to be an xn anyway. P of x1 up to xn, I can write it as a sum of monomials, right? So I have some degrees, d1 up to dn, and I can write it as some coefficients. Now, I mean, something that you have to be a little bit careful about in the finite field setting, that you don't, say, over the reals, is it's possible to write out expressions that are non-trivial where the polynomial ends up being 0. Right? I mean, I have lots of high-powered degree things that I could write out here, and it's possible to write out expressions that look interesting but suddenly evaluate to 0. Right, and since we're going to be operating in this world and we're interested in doing that, we're going to need to be a little bit careful. Now, what's true here is if you insist that all of these d values be at most q minus 1, right? So you just restrict your attention to those powers which are less than or equal to q minus 1. Then things are straightforward. Then everybody behaves nicely. I mean, in fact, if you think about these polynomials, well, actually, how many polynomials of this form do you have where written out in this form? Well, for each, okay. Well, how many monomials do you have? You get to take each of these n guys gets any power between 0 and q minus 1. So the number of terms here is q to the n, and for each of those terms, you get to pick the coefficient. So you have this many different polynomials of this form, well, it's easy to see that any two such polynomials have got to be distinct, because in fact these polynomials with these degree bounds represent all possible functions from f q to the n to fq, right? So I mean, like these guys are kind of formal objects, but each one gives me a function, right? And by just plugging things in and evaluating, and it's fairly easy to see that these polynomials give me any possible function I want from fq to the n to fq. Why is that? Well, it's easy to make a polynomial that vanishes everywhere except at one particular value. Right? If you want to make a polynomial that say vanishes except when x1 equals some particular value, you just multiply through by x1 minus this value you don't want times x1 minus this value you don't want, and so on. That gets you a polynomial of degree q minus 1 that vanishes except when x1 equals your favorite thing. And you combine those for all the rest, and you can very easily write out a single polynomial that's going to be of this form that is non-zero precisely when you plug in a certain value. And because of that, you can get any function you want from fq to the n to fq using polynomials of this form. And that tells you that they have to be distinct, because of course the number of, they have to have distinct evaluations, because this number of polynomials, or sorry, this number of functions is exactly this number of polynomials, right? So I always wonder how much of this I have to say. In some sense, this is all kind of obvious, and but I think it's something we don't deal with frequently enough. So and it can sort of slip by you in the argument. Let me say, in general, what happens if you have a polynomial is you have write out some gigantic polynomial expression. Well, anytime you see some variable raised to the qth power, it's the same as you can just reduce it to the first power, right? Because if you're looking at non-zero elements of the field, well, the multiplicative group of the field has order q minus 1, so anything to the q minus first power is going to be the identity. And so this will be satisfied for any non-zero element, but it also works for 0. So the sort of general process is you have to, if you're working with big expressions over say a field with polynomials over the field of order q, you have to kind of use this identity and to check if things become 0 or not. But the good news for us is we're going to sort of stay in this realm. I'm going to focus solely on polynomials where the expression involved obviously has degree strictly less than q. And then I'm in a really nice setting, because then the only way something can be 0 is if it's obviously 0. Okay. So
you mean you're going to think of the polynomials as functions, not as the vector space of polynomials?
That's right. Right. Yeah.
Thinking of these as actual functions.
Yeah. Will they? Yeah. Well, that's right. Yeah. We'll definitely be thinking of them as functions. We'll have to kind of work with some of these expressions for them. But the good news is it's.
If you said anti-x to the q equals x, this is when you're thinking of it as a function. As a polynomial, this is not true.
That's right. Yes. Yeah. Sure. Yes. Yeah. Right. Okay. So I'm aiming towards this theorem of de Vere. I need one very easy lemma first that tells me that I can construct a polynomial that vanishes on a lot of points if I have enough variables. So let me just. Oh, sorry, I think this is 0. Okay, so what have I written here? So, yeah, so as sort of stated, we're going to be working with polynomials. We're going to be interested in controlling their degrees and looking at what they can evaluate to. So what's happening here, I'm taking some set of points in my vector space over FQ, and this number of points is not too big in comparison with n and d, and the claim is that then there's some non-zero polynomial with degree at most d, which vanishes on all those points. Right. So you can get a polynomial vanishing on a set of points so long as you've sort of got enough enough variables here and enough degree. And the proof of this is really easy. So so again, let me write out again the general form of a polynomial here. So our polynomial p of x1 up to xn, this is going to look like some sum over these d values here. But now I'm interested in degree at most d. So my d values, the degrees will sum up to at most d. And then I'll have a coefficient times x1 to the d1 on up to xn to the dn. Right, so this is just writing the polynomial as a sum of monomials. And I want to think about, I'm trying to make a polynomial here, right? I'm trying to construct a nice polynomial. So what I get to choose here are these c terms, right? So I get to choose these values, but I have to have this property that I evaluate to 0 whenever you plug in these a sub i's. So what's happening So let's think now, these coefficients are what I get to choose. So let's think of those guys as the variables. These coefficients are my variables. And now the constraint is that this polynomial has to evaluate to 0 at a sub I. Right? But what does that mean? Well, you plug in all those a sub I values. Right? So each of these terms you plug in, this evaluates to just some element of the field. So what you get is just a linear equation in these coefficients that has to be 0. So for each ai, the condition that p of ai must evaluate to 0, this gives a homogeneous linear equation on these c coefficients. Right, so for each of these elements in my vector space, my polynomial has to evaluate to 0 there. That's just some homogeneous linear equation in the C's. What you know is that if I'm looking at a whole bunch of homogeneous linear equations and you've got more variables than constraints, then there's a non-trivial solution. That's exactly what I've asked for. So we've got a whole bunch of homogeneous linear equations in those C's. The number of variables is going to be what? So I want to count now the number of variables, the number of ways of choosing n numbers that sum up to at most d. This is one of those problems. So you can imagine taking a sequence of n plus d things where you have d bullets and n dashes. And so I'm trying to count the number of these different terms that I have, monomials, where the sum of the degrees is at most d, right? And the point is that these guys are in one-to-one correspondence with a sequence of length n plus d, where you have n bullets and d dashes like this. And the idea is this would correspond to the term x1 squared x2 cubed, x3 to the first power, x to the fourth doesn't appear. Oh, sorry, x4 to the 0th power, x5. Right, so you get to distribute your D bullets anywhere you like here, and the ones that come after the last bar don't contribute to the, they don't contribute to the degree. Right, so this number of variables here is exactly equal to n plus d choose n or choose d.
N minus 1.
So there's a slightly, usually when you do this, there's like a -1. Only if you were doing this equals d, then this is what you would, then this is exactly what you'd be doing. But I'm going to put in one more dash because whatever falls after, all the bullets appearing after the last dash don't contribute to the degree of any of the terms. So I'm going to do this one. So you get to put down, you get to put down sort of n, so you're going to put down d bullets and n dashes here. And the bullets that come after the last one don't contribute to anybody. But those, so the degree of x1 is the number of bullets before the first dash. The degree of x2 is the number of bullets after that and before the second, and so on. So the number of variables is here. This is less than m, which is equal to the number of constraints. And so by like linear algebra, you get a non-trivial solution, and that non-trivial solution is exactly a non-zero polynomial of degree at most d, satisfying this. Okay.
Do you have some restriction on side d and with respect to q? Like if d is way bigger than q, then
yeah, if that's right. If d is way bigger than q, then this is meaningless. Like, yeah, I'm only going to be applying this when d is less than q, right? Because yeah, and I mean, in fact. Yeah, wait. Yeah, here I really want d. Yeah, I'm going to assume, and I'm going to assume d is less than q. I mean, this stops being meaningful when you take that larger because the polynomials start collapsing, right? This is that. I mean, this is that. We want to. I'm thinking about a polynomial in terms of the associated function, but in order to meaningfully do that, I have to stay in this realm where d is less than q. Yeah. Or at least, I mean, I get you. At least there's a conveniently, if we stay in that realm, everything behaves nicely. That's maybe what I should say. So, right. So we've got this, and let me do Devere. Okay. So. So I've got a subset of fq to the n that contains an affine line in every direction. I want to claim that it has at least this many points. Let's suppose for a contradiction it does not. So in this case, I can choose a polynomial of degree less than or equal to q minus 1 that vanishes on all points by my lemma. Let me say its degree is d, which is at most q minus 1, which vanishes right. So if I have fewer than q plus n minus 1 choose n points, then by this lemma, just taking d equal q minus 1, I can choose some polynomial of degree at most q minus 1, which is vanishing on my entire set. Oh, yes. Yeah. That's particularly important. I mean, I always find these finite field arguments kind of like these finite field polynomial arguments kind of sneaky. And this one hits that as well. So now we're gonna apply this fact that we've got an affine line in our set in every direction. We're going to see what that means in this case. So yeah, let me just start on a fresh board over here. So let's let B be any direction here. So by assumption, I have a whole line in my point set going in that direction. So I can choose some point A in my set such that A plus T times B is in my set for every possible value in the field that you'd plug in for T, right? This is all just what it means to contain an affine line in every direction, right? You choose the direction, I can choose some point so that some point, this will be in my set, so that I take my point and add any multiple of your direction, and I still land in the set A. And now we can consider this function. I'm going to think of this as a function of t now. F of t is equal to my polynomial evaluated at A plus T times B. Right? So now, my polynomial, this is a nice low degree polynomial. A and B are fixed now. I'm going to think of this as a polynomial, where T is the only thing moving. Right? But this is a low degree polynomial. It's degree D, which is less than Q. And, well, by assumption, my polynomial vanished on every point in the set A. And that means that F is identically 0. Right? So this function, F of t, is identically 0. But it has this nice expression as a kind of low degree polynomial. Right? So I have so my function f, it's identically 0, but I have a sensible expression for it as a low degree polynomial. Let me sort of expand this thing, write out what it is. So I'm going to write out p in that same form there. So so what am I going to get? This is the sum as over my possible coefficients of A1 plus T times B1 to the D1 on up to AN plus T times BN to the DN. Okay. So I've got this kind of well, I've got this sensible polynomial expression of low degree for my function f, which is identically 0. Now, if this thing is going to be identically 0, the coefficient of t to the d also has to be 0. So let's focus on that one. So let's just say so 0 equals, let me just write coefficient of t to the d in this, right? So this is this thing that I've written out. It has to have 0 coefficient. Right, so the coefficient of t to the d in this guy has to be 0. Now, the coefficient of t to the d in this actually kind of simplifies this expression a little bit, right? If you want to look at t to the d over here, well, the a terms don't come into it at all, right? I mean, you've got to pick this term every single time. Also, the monomials that are not top degree don't contribute anything. Right? If you have a monomial where the degree of that monomial is strictly less than d, then it contributes nothing to the coefficient of t to the d. Right? So the coefficient of t to the d in this term is exactly the coefficient of t to the d in this same thing where I only look at the top degree terms. So just those that sum up to exactly d, and I ignore the a's. Well, and now you just may as well pull out the t to the d's. This is just equal to this. Well, that's a pretty sensible thing. So let me give that a name. So I'm going to define this p bar to be the polynomial you get by just taking the monomials of top degree. So this is the. I mean, I could just write it as I did there. P bar is just the sum over all those. Oh, I just take all the monomials where the sum of the degrees is equal to d. So sort of in words, p bar is the polynomial you get by just taking the top degree terms from p. And what we've just proved here, I mean now, okay, so now with the help of this lovely definition, what is it that we've proved here? We've proved that the coefficient of t to the d in this expansion, which we know has to equal 0, is also equal to p bar evaluated at b. Right, so that coefficient of t to the d that we were seeking, we know it has to be 0, but it's actually equal to this polynomial, p bar, evaluated at our point b. And that's got to be 0 for every b. But p bar is a polynomial of degree less than q. That can only happen if p bar was identically 0, which can't happen by assumption. I mean, original polynomial was, its degree was d. It's bigger than 0 and smaller than q minus 1. Right? So p bar has to be a non-trivial polynomial, and of degree less than q, and so this just can't happen. And this is a contradiction. And that completes the proof. So, yeah, so that's that. So yeah, this is a really nice instance of some polynomial technique. There are, a lot of questions in additive combinatorics have some approaches using some polynomial techniques. I think maybe we'll do one more in my last lecture as well. Yeah, this is a really particularly clever one, which is sort of why I wanted to do it. It's just so sweet. Everything works so nicely. As I say, kind of the big hope for this finite field version of the Kakaya problem was to get some idea that would then translate nicely to the real setting, and DeVos kind of snatched the conjecture without giving too much insight into that. But the proof is just so lovely. So yeah. Okay, so let me end there. Yeah, so we'll do one more lecture next week where I'll talk about some other kind of additive combinatorics problems in kind of different settings. Next week I'll talk about some ones that are a little closer to my own work. And yeah.